Today's lecture will focus on excitonic and phonon mechanisms in optical absorption in semiconductors. We shall also talk about free carrier absorption and impurity absorption. As discussed in the last lecture, excitons are bound electron-hole pairs which are bound together due to their Coulomb attraction. We have already seen that based on a hydrogenic model, we can get the binding energy of the excitons as minus 13.6 by L squared, where L is an integer, mr star over m0, where mr star is the reduced effective mass, and 1 by epsilon r. So if one was to shine light of energy h nu and excite electrons from the valence band, then due to excitonic absorption, one gets absorption starting not at the band gap Eg, but the absorption will start at Eg minus Ex. This is the excitonic binding energy. So this has been observed in a number of semiconductors and insulators, and as a result, the detailed structure of the optical absorption edge is determined by the excitonic energies. I may give some typical energies of excitons in semiconductors, and we find that, for example, for silicon, the excitonic energy is 14.7 milli-electron volts. For germanium, it's 3.8 to 4.1 milli-electron volts. For gallium arsenide, it's about 4.2, and for gallium phosphide, it's 3.5. Cadmium sulfide is 29, cadmium selenide is 15. Can you suggest why the values are so small in germanium and gallium arsenide and much larger in cadmium sulfide and cadmium selenide? Can you suggest why the values of the excitonic energies are small in germanium and gallium arsenide and gallium phosphide, but much larger in silicon, cadmium sulfide, and cadmium selenide? Yes, due to the fact that the effective masses are much smaller in gallium arsenide, germanium, gallium phosphide. The effective masses of electrons, both electrons and holes, are much larger in cadmium sulfide, cadmium selenide, and silicon. And of course, the dielectric constants are also much larger in gallium arsenide. If you look at this expression, the excitonic energy, if this goes as 1 by epsilon r squared, so if you have a high dielectric constant, Ex will be small. 16 for germanium, but only of the order of 5 or 6 for cadmium sulfide. Right. So that explains the values of the excitonic binding energies. And as is well known, in semiconductors, we are talking about weakly bound excitons, in which the electron-hole pair distance can be much larger than the lattice parameter A. These are also called Mott or Wannier excitons. Whereas the other type of excitons that have been found in alkali halides are called Frenkel excitons, which are tightly bound and they can be considered as located on a particular atom. So these can be considered as excited states of a particular atom. We are concerned with semiconductors, and so the sort of excitons we'll be talking about are mainly Mott or Wannier excitons. As I've shown before, that in the optical absorption edge, just before the fundamental absorption edge, for direct gap semiconductors, one gets small peaks, which correspond to transitions to energies. These are Eg minus Ex, whereas Eg would be slightly higher energy. And in the case of indirect gap semiconductor like germanium, we find that there are steps corresponding to the indirect gap, and there are peaks corresponding to the direct gap. Why is that? The reason is that for the indirect gap transition, one can find a range of k values such that d, dk in the valence band and in the conduction band are the same. So the transitions can take place over a small range of k values, whereas at the direct gap, here the condition is that dE dk is equal to 0, both here and there. So these are called critical points at which one gets peak-like absorptions, whereas here the condition is that dE dk, the slope at the valence band must be equal to dE dk, the slope in the conduction band. As pointed out last time, typical spectra for gallium arsenide, the optical absorption versus energy gives you peaks corresponding to excitonic absorptions at low temperature 28, 78 degrees K. The peaks are much sharper at lower temperature, and the general shift is due to the shift of energy with temperature. As the temperature decreases, the band gap increases. Now, let us come to very briefly a few other types of optical absorption processes. intra-band absorption, that means within a particular band, occurs very often among the valence bands of a semiconductor. Most of the semiconductors we are dealing with are either diamond or zinc blended in structure, and for these there are three distinct valence bands: the heavy hole band, the light hole band, and the split off band, which is split off due to spin orbit interactions. And the split off band is separated from the other valence band at k equal to 0 by an energy which is called delta. Now, in this case, for a p-type semiconductor, the Fermi level can be located somewhere in the valence band if it's heavily doped, and obviously you can see that you can get transitions between fill levels and empty levels from the lower band to the upper band. We're talking about electronic transitions, and for example, one can get a transition from the light hole band here light hole band to heavy hole band there. One can get transition from the split off band to the light hole band, or we can get a transition from the split off band to the heavy hole band. So these are intra-band absorptions which are observed only in p-type semiconductors, because we are not concerned with the conduction band here. This is important sometimes in heavily doped p-type materials, and sometimes this is undesirable, and we want to reduce the optical absorption due to intraband absorption. And one of the ways, as we'll see in the case of lasers, is that we can alter the band structure by having strained layers. We can change this band structure if we apply either compressional or tensile stress, and thereby reduce this sort of spurious optical absorption. Now we come to the next important process, which is free carrier absorption, seen both in N-type and P-type semiconductors. As you know, in all practical devices, semiconductors are doped, sometimes lightly, sometimes heavily, and as a result, there are free carriers that exist, electrons in the conduction band or holes in the valence band. Now, if photons are incident directly, and these electrons can be excited, but however, since momentum conservation is required and photons have no momentum, therefore they cannot be excited directly by a photon, but the excitation must be of this type, which involves change of k vector, and so phonons or impurity scattering must be involved. So it is not a direct band-to-band excitation process like across the valence, from the valence band to the conduction band, in which suppose you have a process like this, a band-to-band process, then as I've shown here, there is no phonon involved because there's no change in k vector. But here, if you have excitation of electrons from a low energy state to a high energy state, or holes, change of k vector is involved, and obviously this involves scattering either due to impurities or phonons. One can, if you fill in the total valence band structure, one can get obviously free carrier absorption of this type either in the heavy hole band or the light hole band. This free carrier process has been studied in the classical Drude model, but using different scattering processes, one can calculate the free carrier absorption coefficient, and this is given by n q squared lambda to the power p over 4 pi squared m star, the effective mass of the carrier involved, refractive index nr c cubed over epsilon 0 into 1 by tau n suffix r. N. This is a refractive index. I'll explain the terms. N is the concentration of free carriers involved. So the absorption is directly proportional to n, and hence this is seen when n is quite large, 10 to the power 17, 18 or more. Q is the electronic charge, lambda is the wavelength, and so free carrier absorption is large at large wavelengths. That's why it occurs in the infrared, where lambda could be a few microns or even 10 microns. So P is a parameter which is determined by the type of scattering involved. In the case of the free electron theory as given by Drude, this free carrier absorption occurs and P is just equal to 2. But if you take into account the different scattering mechanisms, then P is equal to 1.5 for acoustic phonons, 2.5 for optical phonons, and 3 to 3.5 for ionized impurities. To continue, describing the parameters, m star is the effective mass of the carrier involved. Notice this is also a sort of intra-band process. It is not going from one band to another band. It is within a band. Nr is the refractive index at the particular wavelength. C is just the velocity of light. Epsilon 0 is the dielectric constant of free space, and tau is the average value of the relaxation time of the dominant scattering process. So you can see if tau is small, then the free carrier absorption is going to be large, because more scattering means more absorption. So overall, alpha free carrier for a particular material can be given by the sum of these different processes: acoustical phonon, optical phonon, and impurity scattering. These values have been determined for different semiconductors, and one can say that, say, for gallium arsenide, for a carrier concentration N of 1 to 5 into 10 to the power 17, alpha Fc by N is 3, and the scattering parameter P is of the order of 3. For indium phosphide, these are experimental values. The average value of P is 2.5. For germanium, 0.5 to 5. This is of the order of 4. And this is of the order of 2. P is the exponent of the term in lambda, right? So to sum up, free carrier absorption occurs mostly at long wavelengths, and it is important for, again, rather heavily doped semiconductors for large values of N. So again, in lasers, when you have very heavy doping, free carrier absorption may be undesirable, and we would like to eliminate or reduce this. Experimentally, one measures alpha. Say for germanium, alpha has been measured as a function of carrier concentration going from, say, 10 to the power 18 to 10 to the power 20. And specimens with different carrier concentrations and the slope. This is alpha against N. At 4.2 K, and it is found that alpha is roughly proportional to N. Similarly, one can plot alpha against lambda and find the exponent P. Now, I've just introduced the term optical phonons, acoustical phonons, etc. So now let's come to processes that involve these phonons, which are nothing but lattice vibrations, and these can also result in optical absorption, and they can also give rise to scattering, as in the case of Raman scattering or Brillouin scattering. We will mainly be concerned with optical absorption, and to introduce the idea of quantized lattice vibrations, which are phonons, which are of two different types, optical or acoustical. Let us take a look at the typical optical acoustical spectra in semiconductors. This is the phonon spectra. Just as in the case of electrons, we have an electronic band structure in the semiconductor, giving electron energy E versus K. In the case of phonons, we have the frequency versus wavelength dispersion curve, which gives us information about both the energies and the slopes of these dispersion curves. In the case of germanium, we are plotting nu versus K in all these cases. Nu is measured in 10 to the power 12 hertz, and K is normalized of K over K max in particular lattice directions. This is in the 100. I shall explain the phonon dispersion curve for germanium in detail, and then just compare with silicon and gallium arsenide. As you know, for semiconductors such as germanium, which has diamond structure, or gallium arsenide, which has zinc blende structure, there are 2 atoms per unit cell. Each atom can have 3 degrees of freedom, so there are basically 6 modes that can occur. Now, the 6 modes can be split up into 1 transverse and 2 longitudinal optical. One longitudinal acoustical and 2 transverse acoustical. To show the nature of vibrations, one can take atoms, say of different types, a linear chain of atoms, and if the atoms are vibrating such that the displacement is of this type, atoms with different charges all moving in the same direction at one instant of time and then moving in this direction the next instant of time, then these are well-known acoustical vibrations. Right. Whereas if you have the case in which the oppositely charged atoms move in opposite directions, setting up a dipole, electric dipole. This is what is known as optical mode of vibration. And what I have depicted here are both transverse, because the motion of the wave is in this direction and the motion of the atoms is perpendicular. So this is transverse acoustic, and this is TA, and this is TO. Similarly, if the direction of vibration is in the same direction as the motion of the wave, then we have longitudinal acoustic and longitudinal optical modes. So to get back to experimentally determined phonon spectra for, say, germanium, notice that, as I said, that there are two transverse modes, because the atoms can move either in this direction, in the plane of the paper, or perpendicular to this direction. So there are two transverse modes. Okay, whereas there is only one longitudinal mode, because the atoms can move. It's like a sound wave, which is a longitudinal motion. And incidentally, the slope of this LA curve, okay, dw dk, is nothing but the sound velocity in a particular medium. So d nu dk here is the sound velocity. The frequency here at k equal to 0, notice that the TO, LO phonons are degenerate here. This is nothing but the Raman frequency. Okay, this is nothing but the Raman frequency, because when light comes in, TO or LO phonons are excited, and there's a loss of energy, so there's this Stokes shift, and the scattered photon has energy less than this. Now, silicon, being a much lighter atom, has basically the same type of phonon spectra, but the energies are, or the frequencies are much higher because of lower mass. And otherwise, the nature of the curves are the same, and you notice that in the case of these homopolar, perfectly covalent semiconductors, the LO and the LA phonons are degenerate at the end of the blue zone. For gallium arsenide, with masses very much similar to germanium, because the average of gallium and arsenic is the same of the mass as of germanium, the values of nu are almost the same, but gallium arsenide has a certain ionicity. It is a 3,5 compound, so it is not, the atoms are not identical. So one finds that there are subtle differences here. The TO and LO phonons cross at a particular value of k, and the other subtle difference is that the LO and LA phonons are no longer degenerate here at the Brillouin zone edge. This is proportional to the ionicity of semiconductor. What are the energies? Corresponding to nus, one can calculate the energies of these vibrations, and since the frequencies are of the order of 10 to the power 12 hertz, the energies involved are rather small. This is 0.06 eV. This is 0.03 eV. So phonons have large momentum, but the energies are only of the order of 50 or 60 milli-electron volts. If one analyzes this linear chain of atoms, one can actually calculate what are these energies, and for the optical phonons and the acoustical phonons, which are connected by springs of spring constant C. From a simple analysis, one can show that these Brillouin zone edge frequencies are nothing but twice C over m to the power half, where, say, m is the mass of this atom, and twice C over capital M to the power half, where m is the mass of the other atom. In this case, obviously, m is greater than. And at k equal to 0, the frequency of the optical phonons is given by twice C, 1 over small m over 1 plus large M to the power half. So determination of these optical frequencies enables you to find out what are these force constants, C, m and m being known. What are the values of these? As I've said, for gallium arsenide, the phonon energies are typically of the order of 45 to 70 MeV. For silicon, TO phonon has 59.8 MeV, LO 51.3, LA 41.4, and TA 15.8 at the Brillouin zone edge. So, what is the effect of these lattice vibrations? The effect is that one gets function of wavelength. Very strong absorption corresponding to the Westralian frequency. This is called corresponding to the this is the Westralian frequency at which LO and TO phonons can be created by the optical radiation. Remember, the electromagnetic radiation can displace the positive and negatively charged atoms, and one can get a very strong absorption here, which is typically in the wavelength region 15 to 30 microns in the infrared. One point to remember is here electronic excitations are not involved. These are excitations of the lattice vibrations. So there are no free carriers which are created due to this. So to recapitulate, we first looked at fundamental absorption, then absorption due to excitons just near the band edge. We've talked about general free carrier absorption, which is increasing as some lambda to the power p, and this strong Rastrolin absorption is due to the excitation of phonons. We can say a few words about impurity absorption, and then I'll talk about the effective magnetic fields subsequently. Okay. Impurity absorption can be of different types. One can have radiation coming and exciting electrons from donors into the conduction band. This is important at low temperatures because the donors must have electrons. They must not be ionized. The donors must have electrons which are excited into unfilled states. Obviously, this energy is of the order of say 10 MeV or so long wavelength. Similarly, one can have excitation from the valence band to acceptors. The energy is here of the order of 50 MeV. One can also have, at higher energies, excitations from the valence band to a donor level, or from acceptors to the conduction band. So in this case, for example, the energies will be, in this case, the h nu will obviously be equal to Eg minus Ed, or in the case of excitation from the acceptor, h nu will be equal to Eg minus Ea, where this is the acceptor energy. So these will be slightly less than the band gap energy because these values are small. So this absorption occurs in the visible or near the fundamental gap, whereas this type of absorption occurs in the infrared. Excitation from donors into the conduction band or from the valence band to the acceptors are important because this is a method of detection of radiation through photoconduction. I will later on show that this is typical of what are known as extrinsic photoconductors, in which you can get, at low temperature, you can get light giving rise to free electrons in this case, or free holes in this case, and giving rise to electric current. Another type of absorption connected with impurities is donor-acceptor pair recombination, which is important especially in materials like gallium phosphide, in which you have both donors as well as acceptors. Suppose you have donors and acceptors, then one can get excitation of electrons from an acceptor to a donor. So this becomes, suppose this is already has an electron, so the electron is excited from here to here, and this is obviously less than the band gap. The energy in this case is equal to h nu is equal to minus EA minus ED plus E squared epsilon 0 epsilon r into r, because the donors and the acceptors in the solid may be separated by a distance r, and there is Coulombic attraction between the donors and the acceptors. So this is a Coulomb term, and RDA has some discrete values depending upon the lattice. It may be the nearest neighbor distances or multiples of the nearest neighbor distance, and as a result one can find that in the case of donor-acceptor pair absorption, one can get very sharp lines corresponding to different values of RDA, could be R1, R2, R3, etc. So this concludes the discussion of optical absorption processes due to impurities in semiconductors. In the next talk, I will discuss the effect of electric and magnetic fields on such absorption processes.